let's get the show on the road, shall we? So there's an atmospheric boundary layer, and this is what it looks like in idealized conditions. But so when we expect the convective boundary layer in idealized conditions, we imagine convective heating causes mixing that originates from the sun, creating a nice big deep boundary layer that resides as we get the sun setting, and that mixing subsides. But what if we add, oh, sorry. Okay, yeah, I have to do both. Yeah, so once we have the, let's imagine it that we have wind farms in the vicinity, somewhere nearby, but not directly within the boundary layer. How does that impact our boundary layer that's maybe not right inside that area? So we found that previous studies have found that there are some kinds of impacts on the boundary layer when there's wind farms nearby, such as wind speed deficits up to 9%, enhancements in vertical mixing and increase in land surface temperature at night, as well as increase of wakes, which are wind speeds that decrease going through the turbines. Well, wind farms are continuously increasing around the world, and that includes our own neck of the woods of Oklahoma. And so you can see from this graphic that kind of shows the Oklahoma area. We really get this boom of wind farms in the northwest area. And so that's really important to consider when we're talking about different regions that wind farms are popping up, because they have different boundary layers. For instance, we have what's characteristic in our region, the nocturnal low-level jet. And that's just an overnight wind speed maxima that is very characteristic, as you can see from the figure on the right. And so that's a very interesting type of segue into the work that I'm doing, looking at wind farm impacts in relative to the nocturnal low-level jet, because we see that the jet in itself can alter the atmosphere as well. So something that I'm interested in looking at is how the turbulent mixing in particular is impacted both relative to wind farms and the nocturnal low-level jet. So that leads to these research questions. Do northern Oklahoma wind farms induce turbulence? And if so, does the turbulence vary based on nocturnal low-level jet strength? So we had the opportunity to study this with the American Wake Experiment campaign. This was a multi-institutional campaign that was geared at studying wind farms and the impacts on turbine loads, the atmosphere, and many other properties. Huge campaign that took place in northern Oklahoma, and that's just starting to end. For our purposes, we're very interested in the atmospheric boundary layer impacts. So this is a map of where everything is located. So we have here our OU NSSL clamps instrumentation, which we deployed during AWAKEN. And this map shows where those were located. So we wanted to study, we wanted to compare what the boundary layer and its processes looked like both within the vicinity of wind farms and outside. So clamps 1 was placed within kind of nearby around surrounding wind farms, and clamps 2 was placed as far as possible that we could get it away from them, but still within the AWAKEN domain. And so clamps 1 was placed at a golf course, and you can kind of see in this picture on the right the turbines in the background. And clamps 2 was placed at arm site E36. Oh, and also we have other supplementary AWAKEN sites here, A1, A2, and H. That will be mentioned a little later. So in order to answer the first question, do wind farms induce turbulence? We can first take a look at the instrumentation to do that, which is clamps lidars. So peeking out at the top of the trailer of clamps, we have a halo scanning lidar, and from that we can retrieve or we can collect vertical velocity stairs data to compute vertical velocity. And so that's what this first time height cross section here is, along with these black dots of cloud-based height. This is 10-minute average vertical velocity. And we can take that a step further and compute the vertical velocity variance. And that is this equation right here. And that gives us, we can use that as a proxy to measure turbulence. And that's what the second time height cross section is here. And so its square root can also provide a representation for turbulent intensity. And so in order to apply those steps for our purposes, what I did was take the Armadillo Flats turbine, which was closest to clamps 1 and around the wind farms. And I averaged the rotor disc heights that turbine was to the closest usable heights of the clamps lidar. And from that gives us this average sigma W, which is the square root of the vertical velocity variance. And so this is what the winter and summer availability looks like in terms of AWAKEN. So CLAMPS was deployed in the winter of 2022 from October 3rd to December 20th, and in the summer of 2023 from July 1st to September 28th. And so you'll see that in the winter, we were missing quite a bit of data, or we had a lot of contaminated data, both either due to a lot of winter weather that was icy, or we had problems with condensation forming on the inside of the CLAMPS 1 lidar lens. So there's a lot more availability during the summer. And so the filtering done in terms of that data to view the sigma W was looking at only the 0 to 15 UTC period to view the stable ABL and the type of impacts it's having, as well as only keeping cases where both CLAMPS 1 and CLAMPS 2 were available. And then removing suspect data that we saw on the previous slide, days with precipitation and days where flow goes through this red dirt wind turbine that's in the bottom left. So because that's the closest that there might be a turbine impacting CLAMPS 2 if we consider climatologically southerly winds. So we removed days with that, which wasn't a lot, 1 or 2. And so that left total cases from both clamps, 47, 12 from winter, and 35 from summer. And so that's the methodology for answering the first question. And then question 2 looks at the nocturnal low-level jet and how that's assessed. And so also from the LiDAR, we can take plan position indicator scans and process those into VAD scans to get to wind speed. And so that's an example of what that looks like here using a signal to noise ratio filtering palette. So you can see that the nocturnal low-level jet is you can identify it in this plot, but we're also missing some of that data. And so what we can do to account for that is to use an optimal estimation algorithm that was developed called WINDoe, and it works by extracting noise information from extracting information from the noise that's presented that you would otherwise filter out, and it instead uses that to our advantage to estimate what the winds would be. And so that's what I have here in this plot, where it's comparing the signal to noise ratios with WINDoe, as well as its uncertainty measurements. And so as you go up in height, the WINDoe uncertainty increases. Luckily, since we're just interested in nocturnal low-level jet, we don't have to go too high up into the atmosphere. So I employ this nocturnal low-level jet classification algorithm per van der Velde et al. 2015. And what I do is use the same cases that were taken for the sigma W to match them. But here we look only at the 4 to 10 UTC period to kind of make sure we're getting a true nocturnal low-level jet. And then we're also looking below 2,000 meters. So this table describes the classes that are created from this algorithm and the different strengths that are represented for the nocturnal low-level jet. And so for this talk, I'm just using classes 0, 2, and 3. And this is an example of what that looks like. So this is for winter 2022. And to determine what class of a full case would be, because as you can see in class 2, it kind of changes. I use a duration condition where the highest class that lasts at least 2 hours is used, and then if there's none, 1 hour and 30 minutes, and so on. And so we're also seeing comparisons between the VAD retrievals and the WINDoe, and compared to the VADs, WINDoe actually is able to resolve the information a lot better and in a way that makes more sense for these purposes. And here's also a summer example case. Same thing, WINDoe resolves things really well, but now we have additional sites, these A1 and A2 and H sites that also had NROL lidars deployed on them. And so they employ different scanning strategies than we do. They employ 6-beam as a method to collect wind speed with 10-minute vertical stares in between. And they, when they do their lidar filtering, they don't use signal to noise ratio as we do. And so this is basically to say that WINDoe still does a pretty good job of resolving things even under the consideration of different scanning strategies and the different temporal resolutions. So with that in mind, we can move into our sigma W results. And this is showing the clamps 1 and clamps 2 comparisons as columns, and then in the rows are the class 0, class 2, and class 4 nocturnal low-level jets. And so just looking at this, we can see that class 4 has very much a higher amount of turbulent intensity compared to the other 2 classes, and it gradually increases with class. So that's good, that's what we would expect. However, the comparisons between clamps 1 and clamps 2 are not as obvious yet. Going forward, I have the averages of clamps 1 and clamps 2, which are these black lines in one plot. And so we'll be able to see that better. But keep in mind, this is winter when we have a lot less cases as well. Looking at summer, we actually see a lot more of a difference between the 2 sites. Not so much in the class 0, where there's no nocturnal low-level jet detected, but the class 2, we do see that there are more cases with more sigma W mixing that's higher than at the clamps 2. It's actually a lot more collapsed. And then in the class 4, same thing. We see it's just a little more elevated on average, but there are still cases that do dip down well below 0.5 meters per second. But if we combine them, the overall trend is that there is higher turbulence intensity at clamps 1, but it's most obvious in the class 4 regime. And again, you can see a lot of cases are still on the low side, so you can't really pin this happening to an individual case. Anytime it's not a guaranteed, basically. So we can then look at the averages of what all of this looks like. So what I have here is the clamps 1, which is the purple line, and clamps 2, which is the yellow line. But I also separate them by wind direction. And so the solid lines are purely southerly winds, and then the dotted lines are all other wind directions. And if we look closely, just class by class, we can look at class 0. Between the wind directions, we don't see much of a difference. The winter cases, which is the top row, actually didn't have southerly winds. Again, there's only 3 cases here, but summer had a lot more cases, and we still see kind of similar results between the directions. And we actually see here that clamps 2 both in the solid and the dotted lines, have higher turbulence intensity on average. And I did forget to say, this is normalized by dividing by the wind speed that's at the same heights as sigma W, so the rotor disk average. Whereas with class 2, we have some really interesting results here. The non-southerly winds actually are more elevated than the southerly. And there also, what's interesting is there are points where clamps 2 exceeds clamps 1, whereas during the southerly cases, that doesn't really happen as much throughout winter, summer. So I thought this was really interesting. So I took a look at the map a little more. As you can see, there are elevation differences. Not huge, but they might be enough to cause these kind of differences. For instance, the northerly flow might, especially with clamps 2, it has to go through all these crevices here and approaching clamps 2, whereas with southerly winds, the terrain is a lot lower. So that might have an impact as well. For clamps 1, things aren't super different, but even the wind turbines are oriented differently. So even that could be a cause for the difference. So it's something that's interesting to look into. And then the reasoning, I was looking at why sometimes clamps 2 from the northerly direction would exceed clamps 1. Because when there's no nocturnal low-level jet, it's less surprising that they're more, they kind of interchange. But when there is a jet, I would have expected it to consistently have clamps 1 on top, as it usually does. But what I'm thinking is that because it's occurring consistently in the winter and the summer, right around before 10, which is 5 a.m., I'm thinking maybe there's a little bit of a temperature difference because clamps 2 is a little more elevated than clamps 1. Wasn't done yet. And so that's all speculation. These are very new sigma W results, but that's kind of the direction I'm thinking, and I think that'll be really interesting to look into. But going to class 4, actually all the cases were southerly, so there was no northerly cases. And this is where we most see what I expected anyway, where clamps 1 has a pretty sizable difference between clamps 2 for most of the time. The only time that doesn't occur is in the winter. There was kind of an iffy case with the winter though, where we had usable measurements from 0 to 15Z, but it was still like very spotted, and because of winter weather that had happened previously. So I personally, since there's only 4 cases, would take this with a grain of salt. And you can see it kind of like it happening in clamps 2. But I think looking at the overall trend, we can see that there is higher clamps 1 measurements of turbulent intensity. And so with all this in mind, when we are using wind directions that are unfortunately not available during the summer. So we're kind of, to account for that, we're just using clamps 2 as a reference wind direction, but we're just assuming at the moment that the wind directions are the same at clamps 1, which can be justified by seeing that the clamps 1 and clamps 2 in the winter are doing really well in agreement. But going forward, one of the tasks I'd like to do is to look at the wind directions from a site that's only about 2 kilometers to our southeast. And it's called C1A. And it's, I've tested a couple of cases, and luckily they do agree to, if I have the time to go through that. So that'll be a future task. But for now, what I have is to answer our questions. Do wind farms induce turbulence? On average, yes, but there are definite exceptions, such as winter and during certain times of northerly flow, which, as suspected, we think that's due to turbulence. Wind direction is interesting, especially in the class 2. I wasn't initially expecting northerly winds to predominate, but also be kind of more deployed with the intentions to look primarily at the southerly flow, especially because we do have wind farms to the north. So, so it's really interesting that it's showing being more elevated, and that'll be cool to look into. And then we're seeing this turbulence, so does it vary based on nocturnal low-level jet strength? The answer is yes, and in fact, it seems like that's one of the primary factors to cause it to increase. And it's such a distinct increase that at first it's kind of hard to tell if it's if the increase is purely due to the jet itself or just or the wind farms. But because there is a nice difference in the class 4 cases, that kind of helps me to believe that it is a wind farm effect at Klein's 1. So there's a lot of things I can do in the future to look at this. I will do the wind directions from class C1A to be able to really be able to say, yes, that is the direction, at least from an estimate standpoint. Look more in depth at the meteorological processes, such as seasonality, the mesoscale, the synoptic conditions, cloudiness, and then also the nocturnal low-level jet nose heights. I think that's something that'll be really important because as I was going through this, I found a lot of interesting data where the heights, where I was seeing trends where that really depended on the nose. And the lower the nose was, like for a class 4, there wasn't really a difference between the sites, but if it was really higher, we were seeing more of those differences. So I think that would be a really cool future work item. But for now, thank you everyone for listening. I'm so sorry. This took long, I swear it worked. But I appreciate you all coming, and that's what I have. If you have questions, I'll take them. Thanks.
We can open the room to questions, and we can also open questions online as well.
Yes.
For all the cases, really focusing on that question, were the turbines always operating, or were some of the cases they were off?
Yeah. So the non-operating turbines are the gray ones here. That are just consistently not operating. And so there's also to the south this wind farm that's being built but hasn't yet. And so luckily that doesn't impact our AWAKEN measurements, otherwise that would be a problem. But those are the ones that are consistently like not operational. There are times during really high wind speeds that they'll turn off. I think it's past 50 meters per second or miles an hour, but that in these cases that hasn't happened. So
but we haven't really looked into that whether all the turbines were actually in running. So
right.
To look at the state of the
Yeah, so I'm basing that condition just based off the wind speed measurements I did see. So I know for sure that they turn off at a certain point if it passes that threshold. But yeah, as far as like wind turbines for other reasons turning off, we don't know that yet. So
yeah, I mean it could be at the low wind speeds, it could be below the cutting wind speed that they are not turning yet. That could also be a factor. So that's a good point. Francesca should look at that.
Yeah, I also like speaking of the elevation differences, I don't think it would be enough, but I wonder like how much taking just the rotor disk average would affect how much that would play a part if clamps 2 is at a different elevation than clamps 1. So yeah, a lot to look into. So yeah.
We don't have any plans to go back, if that's what you ask. So it's not at the moment.
The second to the last slide.
Oh,
Last slide.
oh, is it
Yeah,
this one?
So you don't have.
No, that side, C1A, somebody else was taking measurements. We were there. So there's no plan to continue the campaign at this point.
Yeah, that's just available during the summer when we don't have data. They have a lidar there that also is collecting measurements. They are 6-beam measurements, so they're only occurring every hour, I think. So they're rough measurements, but in the test cases I saw, it looked pretty promising to use.
I mean, we would need to find funding for that. In theory, we can go back and redeploy. But we would need to. Sorry, so this campaign is ended.
Naive question. The map you showed has quite a bit of, seems to show a bit of terrain between
Yeah.
the two sites. Is there a way you're sort of controlling for that? Or is speed
Yeah,
difference?
not yet. The elevation we've noticed as these AWAKEN results are coming out that it seems to be more of an impact than we thought it would be being deployed in a relatively flat area. We're seeing, like, we just got a paper out where we looked at boundary layer heights based on the fuzzy logic algorithm, which is very much based on vertical velocity data. And we found that regardless of wind direction, there isn't a clear pattern. So we're wondering if terrain maybe has more to do with it than the actual wind farm. So we're looking, so elevation basically is definitely an avenue to consider a lot. I think at least more than I thought it would. It's kind of showing its face more than, and I think it'll be a good thing to approach. So.
Yeah, it seems very challenging. So
Especially since they're so different, just so small of the differences.
I'd like to be able to take the turbine down.
Yeah.
Back up, right?
Right.
Oh, very well. I get to do that if southern portion of the Red River Farm is not to get. Contact.
Yeah, I mean, the central facility, the on-site, and so that purpose as well, because that's been up and running from before the two other turbines that they are. I actually remember when we had made the campaign, we had one campaign in 2012 and one in 2013. My memory serves me well, and when we measured in 2012, there were no turbines, and when we came back in 2013, there were all these wind turbines suddenly popping up. So that's at the central facility, I guess the yellow star, right?
Yeah.
There's some extended facilities as well around, that they have long-term observations at. There would be capability to do some of that, but it just wouldn't be as, dense coverage as we have here. But I believe there's actually a Bantam paper.
looked at this in terms of turbulence.
Yeah,
A really fine terrain.
cases, they looked at that, yeah. And again, some of the work that you have shown questions whether it's really local bursting or whether it's related to the evolution of the lunar jet over the plains. What I find interesting is, since you said, these are normalized data by the mean wind speed. So that actually, if you compare the results then for the different classes, since you normalize by the mean wind speed, so it's here, y-axis label is a bit misleading. It's should be sigma w divided by wind speed, which
Yeah.
but
Sorry, I meant normalized sigma here, but forgot to add it here.
yeah, but what it actually shows is that by normalizing by mean wind speed, the results for the different classes are very similar. So if you look at what you see for, oh no, I'm comparing, I'm looking up and down, so sorry about that. So it goes left to right. So you still see a difference in for class 4 that class, so which would indicate what you were saying at the very end, that probably the shape of the jet also plays a strong role.
Yeah, I think it really
Yeah.
does.
So,
At least when it gets strong.
yeah, when
Yeah.
it gets strong, the shape of the jet. So that is probably something that we really need to look more into, what exactly happens as you have these strong jets, because you do see that increase.
Mhm.
Michelle has a question online. She said, I know you'd be looking into different scale effects. What kind of mesoscale processes do you think may be affecting the turbulent intensity at 2 sites that you're hoping that you may see?
That's a good question. I mean, I'm taking out precipitation, so I'm trying to get those cases as idealized as possible, but unfortunately that reduces them quite a bit. So I'm trying to have like nice high pressure systems without any fronts, but I really have to look into that. I mean, I know for like this winter case day, I know there was lingering of storms in the area, winter storms in the area. And I think, and that's causing that spike in the yellow right here. So I think like that's something to be really cognizant of if I have like lingering impacts just in the area, not even directly above. So I think if I remove those, I'll probably have much lower turbulent intensities. And I think as I include them, they, if I do end up looking more into the different mesoscale impacts, that'll probably increase or make them at least more sporadic as more spikes like this. So I don't know if that answered, but. Okay. Did not die. Cool.
Well, I think the projector maybe has decided that we can wrap up here. But thank you, Arianna.
Thank you.